So in section 3.2, we're going to look at three different things. Two of them are kind of related. One of them is kind of its own thing. But the three things we're going to look at are intermediate value theorem, continuity, and end behavior. So when you graph something on a calculator, most calculators assume that the graph is connected, or that it should be. Especially true for older calculators. If I try to graph, let me show you the graph of something. And I'm going to do it on an older calculator. What I've typed in there is the graph of tangent. It's kind of what it should look like, but not really. Let me show you on a newer one that does it correctly. It should look like that. So it's got these curves to it, but the curves are not connected. The older calculator is trying to connect them, and they shouldn't be. Right? Even this calculator, you can make it so that it looks a little more like that other one. See, now it's connecting everything, and see how fast it draws it? But it shouldn't be doing that. And that's because in this particular graph, there's what we call vertical asymptotes. Okay, you don't have to know about asymptotes yet. But the calculator can detect those things and get rid of them if they shouldn't be there. The downside is you can see how much slower it's drawing it now. It takes a lot longer. Okay. Right. So the point here is there are some graphs you draw that are not connected. They're actually separate pieces. Let's try to graph this one. 1 divided by x minus 3. What value are you not allowed to use for x in the denominator there? 3. So at 3, something weird is going to happen on this graph. Let's take a look. Watch as it approaches 3. It kind of drops off the screen, and it comes back in at the top. So the question there is, could you trace that graph that I have right here without lifting your pencil off the paper? You get from this part to that part without lifting up and putting your pencil back down.
Does this piece of paper go around the world?
No, it's the normal piece of paper.
Okay, yeah.
Okay? No, you can't. And that means something, okay, that you can't do that. So here's a graph that you cannot trace without lifting your pencil because it's two separate pieces. Let's look at the integer function. Okay, I think we've looked at this. Well, maybe we looked at it. I don't know. If we haven't looked at it, you don't have to know too much about it. I just want you to see the picture. You definitely can't trace that without lifting your pencil off the paper, okay? Because it's almost like a set of steps. Now, if you graph it on an older calculator, it'll try to connect those steps, but they shouldn't be connected. Okay, so there's an example of another graph that
you show it like connected.
Connected? Yeah, it'll actually draw it a lot faster too. It's just going to draw it, and it's going to look exactly like steps. Yeah, it shouldn't look like that. It should look like what I had over there. So let's put that there. So there's an example of another graph you cannot trace without lifting your pencil. And this one, you got to lift it a bunch of times. Okay, this other one, you only have to lift it once. Now, this last one is x squared minus 2x plus 4. How about that one? Can you trace that one without lifting your pencil? Yeah, that's a parabola. So you don't have to draw two separate pieces. It's just one big connected piece. So the answers here were no, no, yes. So if you can trace your graph without lifting your pencil, okay, what that means is you have a continuous graph. Okay, so this is the first thing we're talking about, continuity. So if you tell me that you have a graph that's continuous on a certain interval, let's say you tell me it's continuous from 1 to 5. Okay? If you tell me that it's continuous from 1 to 5, then what that means is you could trace from 1 to 5 on your graph without ever lifting the pencil. Okay, so I just used the example 1 to 5, but it could be any. Okay, the point is you can trace from a starting point to a stopping point without ever lifting your pencil. That means your graph is continuous. Or at least that section is continuous. Because some graphs might have small sections you can find that you could trace, but not the entire picture. So you might be able to find a part of the picture you could trace that's continuous, but not always the whole thing. With a parabola, it's always the whole thing. No matter where you tell me to trace on a parabola, from anywhere to anywhere, it's always continuous. If you can't, right, if you try to trace from a starting point to a stopping point, and you have to lift your pencil off the paper to do it, that means it's discontinuous. Any question on that idea? Now, lifting your pencil off the paper, not a very mathematical way to describe continuity. I mean, it gets the point across, it's easy to understand, but I'll show you a more formal definition in a minute. All right, so I want to draw this on the calculator, the graph of 1 over x. And the goal is to find 2 intervals that you can start at and end at, where you don't have to lift up your pencil to trace. And then I want to find 2 intervals where you do. Okay. So this is the kind of graph that you might be able to find some intervals that are continuous and other intervals that are discontinuous. So let's graph it. 1 divided by x. I know something weird is going to happen at 0. Because we can't plug in 0 in the denominator. And that's close to what it should look like. It needs to continue up and down forever. So if I just kind of add to that a little bit, this part should keep going up. That part keeps going right, left, and down. Well, if you notice, I didn't draw it perfect, but it never touches the axes. Okay, as it goes up higher, it just gets closer and closer and closer and closer, but it will never actually touch the y-axis. All right, so let's look at that graph, and let me show you an interval that is continuous. If I wanted, I could trace from there, which is negative 1, 2, 3, 4, 5, 6. I could trace from negative 6 to negative 2 without ever lifting my pencil. I could trace that small section. Now, the way I wrote the interval, I said you could trace from negative 6 to negative 2, including negative 6 and 2. You could also write it this way. That means you can trace from like negative 5.9999999 to negative 1.9999999. Okay. So whether you include it or not include it, that doesn't really matter. But those are continuous. Another interval that's continuous from 1 to 3, 2 to 3, 3 to 7, 5 to 9. Okay, any of those that I just said, you can trace between. But what I want to try to get now is an interval that's discontinuous. Can anybody give me an interval that if you tried to start here and end here, you'd have to lift your pencil to do it? Connor?
Can we go from negative 2 to 2?
Yeah. Negative 2 is right there. Positive 2 is right there. I can't get from negative 2 to positive 2. Remember, you think about like you're driving, right? You got to drive along the graph. Well, there's no way to get there without lifting up and coming back down again. So negative 2 to 2. Doesn't matter if you put brackets or parentheses. Technically, that's tracing from negative 1.99999 to positive 1.99999. Doesn't matter. Anybody give me another interval that if you tried to start here and end here, you couldn't do it without lifting your pencil? Oh, Isaac? Negative 3 to 3, sure. Negative 3 to 3. Basically, as long as your interval does what? You'll always have to lift your pencil in this graph.
Goes from positive to negative?
Yeah, any interval that tries to jump from the negative numbers to the positive numbers can't do it without lifting your pencil. If you give me a positive to start at and a positive to finish at, I can always trace without lifting. If you give me a negative starting point and a negative ending point, I can trace that too. It's just if I try to start at a negative and end at a positive, I've got to jump over that section right there. Okay. So, there's 3 different ways you can have a discontinuity in your graph. A discontinuity is a place where you got to pick up your pencil and put it back down somewhere else to keep tracing along the graph. You can have an undefined value. Okay? An undefined value means a value that if you plug it in would cause you to divide by 0. Anytime you have a function where you could divide by 0, you're always going to have an undefined value there. Another type of graph, a little different, is when there's a break in the graph. Okay, with the integer function, there's no undefined values. Okay, we didn't really study the integer function a lot, but basically what this function is if you tell me a number, any number you want, I'll tell you back the biggest integer I can think of that's less than your number. That's all that that function does. All right, so like if you said to me 3.5, I'd say, okay, what's the biggest number I can think of that's not a fraction, that's less than 3.5? 3. That's what the integer function does. So the question is, if you want to know if you have an undefined value, you ask yourself, well, is there any number that I can think of that doesn't have a number that's smaller than it, that's an integer? No. Any number even negative 106.4. I can think of an integer that's smaller than that number. Okay? So you can plug in any number you want, but it's just the way it rounds, the integer function. You get breaks, or almost like steps. That's where they look like that. And then the last type of discontinuity you can have is a hole. And this is the trickiest one because you can't see it. You have to know that it's there from the algebra. Let's graph this. So if I graph in parentheses x squared plus 3x plus 2 divided by x plus 2. You might think it looks like a line. And from the picture, it does. But let's look at this a little bit. How does the top factor? X squared plus 3x plus 2. Jake? It factors as x plus 1, x plus 2. Look what just happened. You've got an x plus 2 in the top. You've got an x plus 2 in the bottom. Because they cancel out, this graph that I just typed in basically is going to look exactly like the graph of what's left, x plus 1. Okay, watch it on the screen. It traced right over it. The difference between them is that the graph here has a very, very, very small hole in it. You can't see it. The graph of x plus 1, it doesn't. So let me get rid of the one in red. Just go back to the original. There's a hole where you would be dividing by 0. What value of x would cause you to divide by 0 here? Yeah. -2. So if you try to trace to -2, look what happens. There's nothing written for y. If you go to your table and you type in -2, it says error. There is nothing at -2. It's a hole. You can go very close to it. You can go -1.999. That's fine. You'll get an answer. You can even go -2.00001. And that's fine. Okay? It's just, there's a very, 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 very small hole right at -2. So when you're sketching a graph like that, the way we would show it is we draw what we have, put a circle to show there's a hole there, and then continue drawing it. Right? The graphing calculator doesn't do that. And if you zoom in on -2, you'll never see the hole because it's infinitely small. Very, very, very small. Okay.
So wouldn't the third condition be having a hole and the x being not defined be two things that you could technically put together as one? Because in both situations you can't do that because of dividing by 0.
Yeah, these two are both basically dividing by 0. The only difference between them is this one factors into something that's exactly the same in the top and in the bottom. So that's how you know you have a hole. If you can factor and the top factors into exactly what's in the bottom, that's when you have a hole. Watch me, let me mess the top up a little bit. Let me just change it from a +2 to a +3. Now the top doesn't factor. Okay, it doesn't factor anymore. And watch what happens. Just changing one number. Totally different looking. And I have detect asymptotes off, so it actually shouldn't look like that. It should look like that. It's going to draw a little slow.
Really slow.
Yeah, it's much slower. But that's exactly what it should look like. So just by changing that one number, I messed up the whole factoring. Okay? But that's how you know you have a hole. The top factors, and it has a factor in the top that's already in the bottom. Okay. So now, more formally, I could say that a graph is continuous if there are no breaks, there are no holes, and there are no undefined values, rather than saying, I can trace it without lifting my pencil. Okay, so the big boy way to define continuity, there's no breaks, there's no holes, there's no undefined values on your graph. Okay. Okay. Polynomials, like parabolas, cubics, fourth degree ones that can look like this, they are continuous everywhere. In other words, if you gave me a parabola, which is a specific polynomial, I can't find a section that is discontinuous. It's impossible. Because parabolas they're continuous everywhere. So what that means is if you have a function that is continuous from any starting point to any stopping point, then we call that a continuous function. There is nowhere you could ever have to lift your pencil when you're drawing it. Ever, no matter what. Okay, that's called a continuous function. And that's going to tie in with the next thing we look at, which is the intermediate value theorem. Any questions on that idea? Okay, sometimes it's called the intermediate value theorem, intermediate value property. Doesn't matter what you call it. But let me just kind of give you an example of something, and then I think it'll make sense after I give you an example. So one example that I use sometimes is, let's pretend that you had a pot of water, and it started, we're going to start boiling it right now. So let's say at 11:40, we're going to start boiling it, but before we turn the stove on, the temperature of the water was 70 degrees. by 1150, the water reached boiling. It reached 212 degrees. It took 10 minutes. As the water started to warm up from 70 degrees to 212 degrees, think of each temperature that it's going through as it warms up as a number. Okay? How many different numbers or how many different temperatures would the water go through from 70 to 212?
Are we counting decimals?
Including decimals, yeah. Infinite, right? How many different temperatures are you going to go through from 70 to 212? All of them. You're going to go through every single value between 70 and 212. So that means there's a time when the temperature of the water was exactly 190 degrees. There's a time when the water was 150.5, 170.62. You will go through every single temperature. All the temperatures between 70 and 212 are intermediate values. That's what they are. And we're going to go through every single one of them, right? Because boiling water is a continuous process. It doesn't jump. It's not like if you put a thermometer in the water, it would all of a sudden, like, say 70 and then say 100. No, it would say 70 and then 71, or however accurate your thermometer is. It would warm up gradually. Right? And that's what the intermediate value property says. So if you have a function that is continuous on an interval, so just to tie it in with the temperature problem, our interval was a 10-minute interval from 1140 to 1150. You don't have to write this down, I'm just trying to show you. So our starting point was 1140, our stopping point was 1150. So if we have some function that is continuous, then that function will be able to take on every value between the start and the stop. So our start value was 70 degrees, our stop value was 212. So we will go through every single value in between. There's a lot of different processes that are continuous. Like if I were to drop this pen on the ground, right, it starts at a height of like, put it right here, like 4 feet. So it's 4 feet above the ground, and I drop it. Is there a time when it's 2 feet? Yeah. Is there a time when it's only 1 foot? Yeah. Is there a time when it's exactly 1 foot and 1 inch? Yeah. There's a time when it's exactly every single height off the ground between 4 feet and 0 feet. It'll hit every single value. That's the intermediate value theorem, right? Very different than if I said I'm going to like count objects. Like if I start with 0 and I count up to 20, does that mean I'm going to count every single possible number between 0 and 20, including fractions? No, because counting is not a continuous process. It's very discrete. 0, 1, 2, 3, 4. I don't go like 0.1, 0.2, 0.15, 0.16. You don't count like that. You skip values when you count. Okay? So this process doesn't apply when you skip values. Right, so let's look at an example. I have a linear function, and I'm going to look at this function on the interval from -10 to 10. Specifically, I've got a slope of 3 and a y-intercept of -4. I want to know if at some point in that interval I will hit a y value of 15. And if I do, tell me where. Tell me what the x value would be so that you plug it in and get a y value of 15. Well, first thing I want to do is check if that's even possible. Let's see where we're starting for a y value. Let's see where we're ending. And then we'll go from there. So where we're starting for an x value is -10. That would be a y value of -34. I'm ending at an x value of 10. I'm ending at a y value of 26. So I'm starting at negative 34. I'm ending at positive 26. And it's a line. So when you trace from negative 34 to 26, do you ever lift your pencil? No. So it's like, it looks kind of like this. You're starting at negative 34. You're tracing to positive 26 on a line. So am I going to go through 15 at some point?
Yeah.
Yes. At some point, I will go through 15. Maybe right around there. That's what I want to figure out. Yeah.
Where do 34 and 26 go from?
Just plugging in negative 10 into the function and positive 10 into that formula right there for x. Okay. So yeah.
The 15 we're looking for would be on the x-axis, right?
Well, the 15 you're looking for, where the function equals 15. So, like if this was 5, 10, 15, I'm looking for where my graph hits 15, right there. So, I'm looking for an x value. So the question is, if it hits 15 right there, then what is that? What's the x value that would allow me to hit that? So I know I'm going to hit 15 somewhere because I'm going from a negative to a positive. So let's just find where we hit it. Where would I plug 15 into my equation up above? For f of x or for x? For f of x, right. This is the y value. So fill that in right there. And you're going to have 15 equals 3x minus 4. So the math itself here, that's not really hard. It's the concept behind it. Okay? It's the idea of continuity. So we just add 4 and divide by 3. So you will hit a y value of 15 if you plug in, what is that, 6 and a third? 19 divided by 3. So you will hit at an x value of 6 and a third, which is right between these two numbers. And we already knew it would be because we checked the y values. Now, if I said to you, where on that interval do you hit a y value of 50? Well, if you start at negative 34 and you end at 26, you don't. You never go through 50. Right? Any question on that idea? You just kind of have to check your starting y value, check your stopping y value, and make sure that what they want you to go through is somewhere in the middle. If it is, you can plug it in and find it. If it's not, then you say you can't do it. Okay. So the last thing we're going to look at is end behavior. So this is kind of handy because if you give me a polynomial, I don't care how big of a number you give me for an exponent. Let's say you give me 50, x to the 50th power. I already know what that's going to look like. It's going to look something like this. I know that it's going to go down on the left side, and it's going to go up on the right side. And the reason I know that is because, let's change that. Let's make it 51. Now it'll do what I said. X to the 51st power is an odd number, and I know that anything with an odd exponent always looks something like that. Anything with an even exponent, like x to the 10th, looks kind of like a parabola. It might do some twists and turns in here. I don't really know all the fine details, but what I'm focusing on is the behavior on the ends of it, not in the middle. Okay? What's happening on the left and on the right ends. Okay, so let's look at this one. y equals x cubed. So let's graph it, and then I'll explain how we describe the end behavior. So here's the graph of y equals x cubed. Now, I'm going to translate what this says on the right-hand side literally, exactly how you read it mathematically, and then I'll kind of reword it to more common sense kind of words. So what the top one says is the limit of f of x as x approaches infinity. And that's a question. What is the limit of f of x as x approaches infinity? The bottom one says, what is the limit of f of x as x approaches negative infinity? Now, if I reword that, what it's basically saying is, what is happening to y as x gets bigger and bigger? That's what it's asking. What's happening to the y value as x heads further and further and further to the right? So let's look at it. If you look at that graph, what happens to your y value as x heads further and further to the right? Yeah.
It gets bigger.
It gets bigger, and what's it getting bigger and bigger to? It's getting closer and closer to infinity. If I look at my table, look at what happens as x gets bigger and bigger. If x is 10, we're at 1,000. If x is 15, we're up over 3,000. If x is 25, we're at 15,000. As x gets bigger and bigger and bigger, y just keeps getting bigger and bigger and bigger, and it's not slowing down at all. Now, how about the other way? What's happening to y as x heads further and further and further to the left, okay, towards really, really big negative numbers? Okay.
To the left.
Yeah.
It just gets closer to infinity.
If it was getting closer to infinity on the left, it would have to look more like this. It would have to be more of a U shape.
Negative.
Negative infinity, yeah. So what's happening to the y value as x gets more and more and more negative? We're getting closer to negative infinity. So another way you can describe what we just said right here is with these arrows. The arrow on the left tells you which way the graph, that's fine. The arrow on the left tells you which way the graph is going on the left side. It's going down. The arrow on the right tells you which way the graph is going on the right. It's going up. So the two choices, you have up and down for the first arrow, up or down for the second arrow. So what does that mean about how many different combinations you could have? This is one of them. Mike?
Up on the left and down on the right.
Yeah, you got up on the left, down on the right. So how many different combinations in total?
4.
There's 4. Yeah. 4 different combinations. Both up. That's like your parabola, right? Something of that shape. Both down. Okay, even something like that. It does some little twists and turns in the middle. Who cares about that? It's going down on each side. Okay. Down, up. That's like the one we just did. Again, take as many twists and turns in the middle as you want, but overall, down left, up right, up left, down right. So there's only, for polynomials, there's only 4 types of end behavior. And you're looking at all 4 right there. So sometimes we use the arrows to describe it. Sometimes we use that limit notation. At first, some people find the limit notation a little bit, different. But it's really the same thing. So let's look at a table that tells us exactly what the end behavior is going to be based on only 2 things. The highest exponent, okay, so that's your highest and that's your leading coefficient. If the highest exponent is even or odd, that tells you something. And then if the leading coefficient is positive or negative, that tells you the other thing. Even exponents always have the same behavior on each end. Up, up, or down, down. If you don't remember that, just think of the most basic one you can. Think of y equals x squared. X squared is a parabola. It's a U shape. Squared is an even power. Up, up. Okay. If you have an odd exponent, that's when you get one of each. Okay. Odd exponents go up on one side, down on the other. Which side is up, which side is down, that depends on the leading coefficient. If the leading coefficient is positive, you get the upper right case. If the leading coefficient is negative, you get the one on the lower right. Okay, but that chart will tell you what the end behavior is going to be. Any question on the chart? Okay, so we're going to look at a couple examples on just graphing something and see if we can figure out the end behavior. So all you're looking at here is the leading term. 8x cubed, 4x squared. If you've got all that stuff, that minus 4x squared minus 5x plus 6, yeah, that's great, but it doesn't mean anything. Okay, the only thing that matters for figuring out the end behavior is this, right there. None of that other stuff makes any difference at all. It might cause little twists and turns. I'm not saying this doesn't affect the details, like the small details, but big picture, the first term controls the whole polynomial. It's got the highest exponent. It's in control of what the polynomial is going to look like. Big picture. Okay. That's what I just said. So that thing I put a box around right here, 8x cubed, for this particular problem, that thing written in red, what's in the box is called the end behavior model. It's the end behavior model, which from now on I'm just going to abbreviate EBM. So if you get a problem and they ask you to find the end behavior model of some long polynomial, what I have right there is basically like something in red right there. The only thing you have to look at is the first term. That's it. Just write down the first term. That's the end behavior model. As long as the first term is the highest exponent. Okay, if they do something tricky and write it out of order, then you gotta watch for that. But in general, I don't do that. So. All right, so what I'm going to do is I'm going to graph a function, and I'm going to graph just its end behavior model. And I want you to see if they look kind of similar or they don't. All right, so let me just move that up a little bit. So I'm going to graph 2x cubed minus 7x squared. I'm going to get rid of that. So 2x cubed, 2x cubed minus 7x squared minus 8x plus 16. And now they're telling me a window. They want me to graph it using that window. Actually, two windows. First one they want me to try is negative 8 to 8 and negative 100 to 100. Let's try that. Negative 8 to 8 and negative 100 to 100. I'm going to hit graph, and I want to see how similar they look. Okay, there's f of x, and what's in red is g of x. Do they look exactly the same? Not quite. The blue one has some twists and turns in it, the red one doesn't. But they don't look the same because we're zoomed in, we're looking at the detail. Let's zoom out. Okay, so instead of looking at all the little details, let's get a bigger picture of this. Negative 40 to 40. Negative 10,000 to 10,000. I'm graphing the same two things. I didn't change anything that I'm graphing at all. Look at how they look now. How do they look now? They look almost the same. I mean, they're not exactly the same. We know the blue one has some twists and turns, but we're focusing on the big picture. And the first term always gives you the big picture. Right? So if I was going to graph number 7, what would I graph to get an idea of just the big picture? Negative 0.5 x to the 4th. That's going to control what that whole graph looks like. And now, can somebody tell me what the behavior would be? Would it be up, up, down, down, up, down, down, up? What would this one be? It's an even exponent, negative number in front. Down, down. Yep. I don't know exactly what it's going to look like. It might do some little twists and turns in there. But overall, it's going to be pointing down and down. Okay. Any questions on that? So that's the last 3 things that are on the test. Idea of continuity, intermediate value, and behavior. So homework is on page 161. 1 through 5, 9, 10, 12, 15, 16, 21 to 25, and 29 to 31. Okay, don't forget, I will be after school today. If you need to make up any tests from last academic week, today's the last day to do it after school. If you're not going to do it today, then you either got to do it tomorrow or it is a 0.